Hi there, welcome back to the formulaic approach. Now in this video, we are going to be talking about non-metals. Now I promise you, this video is going to be long first, but make sure to stick till the end because I'm going to be unpacking everything that you need for your exam for under hydrogen, oxygen, chlorine, and nitrogen and carbon. And I'll treat it in a way that you will understand, that you would not really need to cram. Do you understand? So make sure you stick with me from the beginning to the end. Now, if you already know about the difference between non-metals and metals, you can skip rather to where I started with hydrogen. Okay. So I'm going to start from scratch so that you can understand and build it up. Okay. Let us begin now. So we have to understand the difference between metals and non-metals. Those are the two major divisions of the atom that we have in the periodic table or on the periodic table. So now our periodic table is going to look like this. Okay, so we have metals, hydrogen, helium. Now we have metals, lithium, beryllium, all of those. We have metals on somewhere around here, and we have non-metals on this other side. Exactly. So I'm not drawing it for you. I just want you to see the position of the metals and non-metals. Now, we have the differences between non-metals and metals. Let's quickly compare them so that you know the fundamental difference between them. Now, what is a non-metal? A non-metal is a chemical element that will ionize. It ionizes with or by a gain of electron. By a gain of electron. That's the way we practically define them. While these ones, they ionize by a loss of electron. Exactly. Why is that so? Let's pick sodium, for example, that will be around here. Now, sodium is here. It will be number 11. Now, using the shell model that was propounded by this woman, Frey, it says that or you call it the octet rule and duplet rule. Octet, duplet, or duet rule. So it says that an atom is such that there is a nucleus and electrons around it in shells, right? So now, if you want to draw the shell model for sodium, it will look like this. Like I said, if you already know this, just skip ahead. But those that don't know it, don't worry, you will not be lost. Just continue with me. For sodium, for example, is going to look like this. The first shell can take 2. Second, the remaining shells will take 8. So we have 2 electrons here. In the nucleus, don't forget, is where we have neutron and proton. Electrons are the one we arrange here. So we have taken 2 out of 11 to remain. This is sodium, this is the nuclide. This is where we write the nuclide. This 23 as the mass number. Don't forget, mass number is denoted by A. Don't let it confuse you. Atomic number is Z. Okay? You would have thought that they should put A for atomic number, but no, Z is atomic number, A is mass number. This is nuclide. It's called a nuclide. Okay, it shows the diagram that shows the mass number and atomic number of an element. So it has 11 protons and 11 electrons. Those 11 electrons will be when this guy is in the ground state. So this thing I'm drawing is for sodium in the ground state. Ground state means unreactive state. So we have taken 2 out of this. Remain 1, 2, 3, 4, 5, 6, 7, 8. We have taken 10 now. 8 plus 10. This is the L shell. In the M shell, it's remaining 1. So that one, let's fix it here. Now, that one electron is the last electron, or is the only electron in its outermost electron shell. So we call it the valence electron. The valence electron is the last number of electrons, the electrons in the last shell. Exactly. So it has 1 here. And for this guy to be stable, it has to react. So by reacting, how does it react? It will react by giving away electron to someone that needs it. Exactly. How many electrons is it going to give away? It will give 1 electron so that to attain stable octet state. Exactly now. So by giving away that electron, it has lost the electron. So it will become an ion. So this guy, Na, being a metal, will lose ion. So look at lose electron. How many electrons is always 1? It will lose, that's minus E, right? To become Na plus. Now listen, in chemistry we don't use minus. So the way I teach my students to do it is, this is losing, right? So you now bring this guy here. So it will now become Na to give Na plus plus E minus. Then you might not think, how do I know which one is metal? How do I know which one is not metal? I've told you before in my other videos that any element that is ending with ion, apart from helium, is usually most likely on your first strength element is most likely a metal. In fact, it's going to be a metal as far as it's in your first strength element. Any guy that ends with ion, sodium, potassium, calcium, those guys, magnesium, they are what? Metals. Then non-metals are the ones, I said these ones, they end with ion. These ones practically end with gene and ion. Exactly. So most ones that end with gene and ion in your first 20 elements, they are mostly what? Metals. Alright. So seeing that we now know this, now look at the ionization. Sodium became Na plus. How many electrons will now be here? 10. So to have the same electron configuration as neon. Neon is the guy that is stable. Neon is the guy that will meet here just before we get to sodium on this side. Exactly. All these guys are group O or group 8. The group O means they have no valent electron. I mean, their valence shell is balanced. Do you understand? So they are non-reactive. We call them inert gases from the word inertia, physics, which means lazy, right? Unwilling to react. So they are called noble gases or inert gases or even rare gases. So this guy retain the same electron configuration as neon. So how did he ionize? It ionized by a loss of electron. Look at the way I did it too. So overall, electron will now be on that side. So now listen, we said loss of electron, Leo. That's how I teach my students. I tell you to do it this way. And gain of electron. Now, you remember Leo, that's for lion, right? Panthera Leo, okay? So loss of electron, oxidation. Now, what does a lion do? A lion roars. How does it roar? It roars like, oh, right? So that's grr. Exactly. Gain of electron, reduction. So these guys are reduced. These guys are what? Oxidized. So the guy that is oxidized is always the reducing agent. The guy that is reduced is always the oxidizing agent. So non-metals are oxidizing agents and metals are what? Reducing agents. Now, also seeing that electron is on the right. I've taught you all this in electrochemistry. So make sure you see my video. I will link it in the description. And the first comment. Once you see that is in the electron is on the right side, that is what? Oxidation, when the electron is on the right side. But if electron is on the left side, as we'll see in the one I'm going to draw here now, that is reduction. So let me show you, how does this guy get ionized, non-metal? I like to pick, let me pick chlorine, very simple one. Now, chlorine is going to get ionized how? By a gain of electron. So this guy gains electron. When you gain, that's added, right? Electron is added onto you. So you become Cl minus. Exactly, Cl minus. Now, but the way this guy forms, this guy's chlorine does not exist as just monoatomic molecule, monoatomic gas. It is a diatomic gas. So notice that I put H2O2 Cl2N2. That's the way they exist as gaseous molecules. They are diatomic. You say they are what? Diatomic. Make sure you're listening to me, be taking notes. So this guy will be Cl2. Now there are 2 atoms of chlorine here. Balance it here. 2 atoms of chlorine. Now, but the total charge here will now be what? -1. And the total charge here is what? -2. So we have to balance it by putting 2 here. That will be 2 times E minus. And it is E minus, not E minus 1, because we don't write the 1 since it is 1. You know, just like mathematics, x is the same as 1x, so we don't add the 1. So that's the same reason here. But if it was magnesium, for example, that was ionizing here, it would be Mg, total electron here, 12. But by the time it loses electron, it usually loses 2 electrons because it's in group 2. This one lose 1 electron, this one lose 2 electrons, the other one lose 3 electrons. Are you getting it now? So it's in group 2, it's going to lose 2 electrons. So by losing 2 electrons, it will become Mg2 plus. Is that clear? Then this guy will now go there. So it now becomes Mg to give Mg. You don't need to cram where will you put electron. Just remember, gain is addition. Loss is minus, but we don't use minus in chemistry. Put it on that side. It becomes positive. The way we do crossover in maths. So 2E minus. Exactly. So this is the way this guy gets ionized. Now, Do we need to balance out? Let's see. What's total charge here? 0. Total charge here plus 2 minus 2, 0. Do you now understand? Let's do one more gas. Look at oxygen gas, for example. Oxygen gas. When this guy gets ionized, it's ionized by gain of electron. When it gains electron, it becomes O2 minus. So now, I told you that they are always diatomic, so you put 2 here. Seeing this, there are two atoms of oxygen here, there must be 2 here too. This one is charged, not the molecular number, not the number of atoms. So the charge is not this. This one is 2 oxygen atoms. This thing means oxygen O2 minus and O2 minus, 2 of them. That's 2 of them. Is it clear now? So from here, we'll now balance. Here, total atom is 2, total atoms 2. Here, total charge minus 4. Because this is minus 2 minus 2, that's minus 4. Just do 2 times 2, that becomes minus 4. 2 times minus 2, minus 4. And remember, we write the number before the charge. Number before charge. So here, we have, how many electrons do we have there? You know, this is minus 4 here. So we now need 4 electrons, so that minus 4. So that total charge on either side is balanced, minus 4 and minus 4. Is it clear? Now, that is for the ionization. Another difference between them is that metals are generally hard. They are generally what? Hard, and they are generally hard solids at room temperature. Room temperature is between 25 to 27 degrees Celsius. But these guys, non-metals, they are generally soft or liquids or gases. Soft solids or liquid or gases at room temperature. But these ones are generally hard. But there's an exception for the metals. This guy is not hard. Mercury is the only one that is liquid at room temperature. Mercury is the metal that is liquid at room temperature. Don't forget that, please. Then this one, there's also exception, the ones that are not soft. In fact, it will shock you that the hardest substance is not even a metal. The hardest substance in the universe, in the earth, is diamond. And diamond is under a non-metal. It's an allotrope of carbon. We're going to treat it. Just stick till the end. Diamond is the hardest substance. Graphite is also hard. Or no, it's actually soft, but it's also solid at room temperature. Now, the next one is this, that these guys generally, they conduct electricity. They conduct electricity. And they are good conductors of electricity. Now, there's an exception also. The exception here is lead is not a good conductor of electricity. It's not a good conductor of electricity. They also electricity. Now they are also good conductors of heat. That's metals. They are good conductors of heat, except this same lead and gold is not a good conductor of heat. But these guys, but the remaining, in fact, the best conductors of heat are copper and aluminum and which other one for heat. That's why we use zinc also. Zinc. That's why we use our zinc for making our utensils that we use in the kitchen. Do you understand? Because they are good conductors of heat. Then these ones are generally poor conductors of electricity and poor conductors of heat. Okay, but the exception is graphite, another allotrope of carbon. This one conducts electricity. It's a good conductor of electricity. Alright, so that is it for metals and non-metals. Now let's begin our first non-metal. Now, our first non-metal, let's take hydrogen. Now, hydrogen was discovered by Henry Cavendish in the year 1766. Okay, Henry Cavendish discovered it in the year 1766, but it was not until 1772 or so where that Antoine Lavoisier was the one that now named it. He named it in 1772, and he named it hydrogen because of so there are two words here. Hydro means water, and gene means what? Former. Water former. Is it clear? Now, water former. Now, Now, let's now talk about the things you have to know about hydrogen. Now, remember that know first that hydrogen is the most abundant gas in the universe, or most abundant element in the universe. In the universe. Universe means the world, the earth, the other planets, the heavenly bodies. Do you understand? All together is hydrogen. Don't misplace it too, because when we get to oxygen, we also say it's the most abundant. But in the earth crust, exactly. So this one is the most abundant in the universe. And we see that as the case because the sun is greater than all planets. Yet, all planets combined, yet 90% of the sun is hydrogen. It's hydrogen gas. In fact, all the stars, their light is because of burning of hydrogen. Do you understand now? So hydrogen is what is makes up the light of the stars. So basically, it is the most abundant element in the universe. We also see it occurring in water. Do you understand? Now there are three allotropes or three allotropic forms of hydrogen that you need to know. Three allotropic forms. Now first, what is allotropy? Allotropy is a phenomenon where, this is the only time I'll define it though, because we also see it in others. Allotropy is a phenomenon where a substance exists in different forms in the same physical state. It has different forms, it exists in different forms, but in the same physical, what we can see. So for example, the first allotrope that you should know is protium. Protium. Now, protium is the lightest isotope of hydrogen. Why is it light? Look at the nuclide. The nuclide looks like this. Then, this guy, the second one is deuterium. Okay, this one we use P to denote it, this one we use D to denote it, and tritium. This one we use T, capital T, to denote it. Now, tritium is one that forms heavy water. The water we drink is formed by protium, H2O. But this one forms heavy water, D2O. That's heavy water, don't forget. Heavy water. Now, this guy, the nuclide looks like this. H2 and 1. Now, remember that this is the mass number, like I told you. Mass number, atomic number. Atomic number is the number of protons. So how many protons will deuterium have? 1. How many? Then mass number is equal to number of protons plus number of neutrons. So here, since you are seeing 2 here and 1 proton is here, then it means that this mass number is 1 proton plus 1 neutron. Exactly. But here, now, number of protons is 1. So it means the only gas that this guy have in his nucleus is a proton, no neutron. Don't forget which allotrope of hydrogen does not have a neutron. It is protium. So it's only proton that it has. Then tritium is the nuclide looks like this. It's going to have what? Since you are seeing 1 proton here, then it means it has 1 proton but 2 neutrons. Is that clear? 1 protons, 2 neutrons. See my video on nuclear chemistry and physics to understand better. Because this guy is radioactive. This guy is unstable and radioactive. Radioactive. I explained why in my nuclear chemistry and physics video. All right. I'm calling you that because I did it together. I started with chemistry, then we went to the calculation in physics, nuclear physics. It's more tilted towards physics than even chemistry. But let's go on. So that's the point. Those are the allotropic forms of hydrogen. Now, what are the physical properties of hydrogen? Number one is that the physical properties. Now, number one is that it is the lightest gas known. Don't forget that. It is the lightest gas known. So, if a gas is light, what will be the implication of that? The implication of lightness is that it will be collected by upward delivery. It will be collected by what? Upward delivery or downward displacement of air. Don't forget that. See, when you collect a gas by upward delivery, another name for upward delivery is what? Downward displacement of air. Downward displacement of air. I'm going to explain how. Of air. What that means is this. If I have a gas cylinder, a gas jar rather, and I put oxygen, I put hydrogen here. I now use another gas to another this thing to cover it. You see this thing here, there will be air here, there will be air here. So initially there's hydrogen gas here. After a while, hydrogen will come, air will come down, hydrogen will go up. So it means that air is displaced downward, hydrogen is displaced upward. Is that clear? So upward delivery or downward displacement of air. It means that if something is heavier than air, denser than air, that's how to think of it. That's the word, denser than air. But the way to think of it is heavier. Is that clear? So heavier than air, it means that that thing will displace air where upward, and the gas will what come down. Example is um, chlorine. Exactly. Chlorine is 1.7 times denser than air, so it will be collected by downward delivery or upward displacement of air. Exactly now. So it is the lightest gas known, and it is colorless, odorless, and tasteless. That's by the way. It is slightly soluble in water. So because it is only slightly soluble in water, we can collect it over water. But gases that are soluble in water, moderately to highly soluble in water, we cannot collect them over water. That's the implication. Then another physical property is that since it is a light gas, it is slightly soluble in water, it is colorless, odorless, and tasteless. It is what else? If I remember any other thing, I'll let you know. Now let's talk about before we talk about the chemical properties, let's talk about the laboratory. No, let's talk about the chemical. We'll do the laboratory preparation later. Chemical properties. Now, what are the chemical properties of this guy? The chemical properties of this guy is that number one, this one is his test. It can ignite, it can extinguish a glowing splinter. So it doesn't support combustion. Don't forget, it extinguishes a glowing splinter, with or a glowing splint with a pop sound. A pop sound. So meaning that if you insert, let's say inside this my jar, for example, there's hydrogen, and I expose a glowing splint to it. A glowing splint is if I burn this thing now, if I burn it and it's burning not so brightly, just lightly, and I'll put it here, it will extinguish it, it will kill the fire with a pop, a mild explosion. Exactly. But not explosion. This time it is extinguishing it. It kills that fire with a pop sound. Exactly. With a pop sound. Now the second thing with hydrogen is that hydrogen has a reducing property. It has a what? A reducing property. I mean, it's in group 1, so it will have a reducing property. But in the presence of a stronger reducing agent, it will be oxidized. For example, if you react sodium, which is a stronger reducing agent, plus H2 gas, it will form NaH. Do you understand now? So you balance. So this is a stronger reducing agent. So this guy is reduced itself. Hydrogen is reduced here. So it is acting as an oxidizing agent here. So but it has reducing property. It reduces substances like for example, if you react what is it called now? Reducing property, its reducing property is just its ability to remove oxygen from any component, any gas, exactly, or any substance. It will remove oxygen from it. All right. So another chemical property that we need to know is hydrogen. Okay, let's go to the laboratory preparation already. The laboratory prep. Now the laboratory prep will be such that we will for hydrogen you you use I've talked about this in salts. You will use the action, or that's the way we put it, action of a metal on a dilute acid. Do you understand? The acid must be dilute. For example, dilute HCl. Is that correct? So for example, the classical one we use is zinc. Now you ask me why is it always zinc? Now we don't use sodium for example because his reaction is harsh. Do you understand? Because it's very reactive. Do you understand? But this one is can be performed by students in the laboratory because this one is moderately reactive. So if you react it with HCl, what you will get is zinc chloride and H hydrogen gas. Is that clear? So hydrogen gas will be given off. Is that clear? So how is the setup like? You are going to, you know, add into maybe a flat bottom flask your zinc and your HCl dilute. HCl will be here, then your zinc will be added. What will happen is that you are going to collect this guy in a pneumatic trough. You are going to collect it in a pneumatic trough. The reason is it is not soluble in water. You know, pneumatic trough looks somewhat like this. Exactly. This is a pneumatic trough. We call it pneumatic trough. And a beehive shelf is put here, okay, to allow for only oxygen to go out, to go into this place. Exactly. A beehive shelf. We call it a beehive. It controls what gases is allowed. Do you understand? Do you understand? Beehive shelf. It is used to collect gases in the laboratory. So the point is that your guy will make it through here, your hydrogen will make it through here and be collected over water. So what you have here is your hydrogen gas. Don't forget. But when you collect it over water, you know some droplets of water will be on it, some molecules of water. So you need to dry the gas. So in the laboratory, um, 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 we use calcium chloride to dry it. So in your exam, you're going to say a diagram like this, for example, you say a diagram like this, then hydrogen gas. So you now see fused calcium chloride, fused calcium chloride. You see the molecules here, okay? The chunks here rather. And our collecting jar, our gas jar will be here. So dry hydrogen will be here. Don't forget, dry hydrogen. Then our wet hydrogen will be passed into this place, wet hydrogen. And this guy is CaCl2. So it is used to dry the hydrogen gas. All right. So that's the laboratory preparation. Other methods of preparing hydrogen. Before we get to the industrial preparation, other methods include this. Now watch. You see, let me quickly show you something. You remember the electrochemical series, you are going to need it a lot. So maybe I'll just put it here on one edge here. We have potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, hydrogen, copper, mercury, silver and gold. So this guy plus, 2 plus, 2 plus, 2 plus, 2 plus, 3 plus rather. 2 plus, 2 plus or 3 plus, 2 plus, 2 plus, plus, 2 plus, 2 plus, 2 plus, plus. Now watch. This series is very important. I'm going to need it a lot for all these guys. You are going to need it to answer many questions here. Now watch. You see, these two guys, they can react violently with cold water, even cold water. Cold water. So if you react this guy with cold water, you'll be hearing explosion, mild explosion. Like you'll be hearing the sounds. Pa, pa, pa. Do you understand? There's a video on YouTube that I showed my student at one time about the reaction of this guy and this guy with cold water. So, but the rest, these ones, they react with warm water. They react with what? Warm water. These guys. So when these guys react with cold water, for example, Na plus cold water is going to liberate hydrogen and form the oxide of this guy to liberate hydrogen. But you don't react it with warm water because it will be more explosive. But then if you now react it with, you now react these ones with warm water. So these ones cannot react with cold water. They will need to, you have to warm the water for it to react. Then in fact, Iron is a classical one we use. Iron filings will be set somewhere here and it will be heated. Then water will be somewhere in another jar. It will be heated. Okay, so there's steam. Not yes, steam is actually hot water. So this guy is here basically reacts with hot water because it's steam that will make it so here. Do you understand? So steam is what will make it here and it will be collected over water. The hydrogen will be liberated. So for example, for iron, it's going to be Fe plus H2O and it will give you Fe3O4 plus H H2 gas, exactly, which will be collected over water and dried again using fused calcium chloride. So that is their reaction. Then these ones, they don't displace hydrogen. Keep that in mind. Only these ones on top can displace hydrogen. These ones that are here can displace hydrogen. But anything below it cannot displace hydrogen. Cannot displace hydrogen. But there was one question I saw in one exam one time. I can't remember which exam that is. That which of these can displace hydrogen? And they mentioned all this and copper. So they mentioned a kind of solution wherein hydrogen is being displaced. Now, I told my students that they should pick the answer copper. Why? Because copper is, you see that their reactivity is very close. So if anyone should even displace hydrogen from any solution at all, it will be what? That copper. Do you understand? Because it's very close to it. So that makes sense. Do you understand now? But neither of this can displace hydrogen. Now, let's talk about the industrial preparation of hydrogen. Now, it is prepared industrially using the Bosch process. Okay, quickly write the following processes down, then we'll continue. We have Bosch process, we have Solvay process, we have Exins process, we have contact process. Which one again do I remember? Ostwald process. Okay, these are the ones that they commonly ask the most. So ABAS process, that's for nitrogen that we'll deal with. Now, Bosch process is used for preparing hydrogen, exactly hydrogen gas. Solvay is used for preparing Solvay. Wait, let me remember this one. Hexene is for graphite. Okay, contact is H2SO for everybody knows that one, right? Ostwald is HNO3, everybody knows that one. See? Haber's process is for this guy ammonia. Do you understand now? Ammonia and nitrogen. Now, Solvay will be for sodium solvate. That's how I remember. Sodium carbonate. Exactly. That's the way it is produced in the industrial production. So, but we are dealing with Bosch process. Now, make sure you have put it down. Put it down. Now, Bosch process. The Bosch process involves passing steam over coke. Passing what? Steam over coke. When you pass steam over coke, this gas. Okay, when you pass steam over coke, it will produce carbon monoxide plus hydrogen gas. Together, they are called the water gas. They are called what? Water gas. There's one question that is commonly asked. We'll do it again in carbon. I'll just brush over it because I've talked about it here now. There's water gas. There is synthesis gas. It's also called syngas. Synthesis gas or syn gas. Exactly. That one has the formula CO plus higher molecules higher molecules in number of hydrogen gas. Exactly. So don't mistake it. This synthesis gas. Water gas can be gotten from synthesis gas. While producer gas is this one. CO plus N2. Don't forget it's not CO2. It's not CO2. It is CO plus N2 producer gas. CO plus H2 water gas. So this is how we produce this guy in the laboratory. When you pass steam, heated water over coke, this coke here. Now, the second way we produce it industrially is by action of water on the same steam on methane. Okay, on methane. When you combine this guy gives you CO plus 3H hydrogen gas, and this is synthesis gas that I talked about. So don't forget. So that's how we prepare it in the laboratory, in the industry. All right. Now, what are the functions of hydrogen? We use it for oxyhydrogen flame. Don't forget oxyhydrogen flame. It burns. Hydrogen generally burns as it is colorless, okay, but chemical property. It burns with pale blue flame. It has pale blue flame when it burns. Is that clear? All right. Now, um, so it is used for oxyhydrogen flame. It is used for filling balloons. It is also used for production of HCl, and that's primarily the uses that you probably need to know. If I remember any other one, because they are intertwined. So I might be remembering some things later on. I will add to the note. Now let's go on. That's why I'm treating them together. Let's go to oxygen. We are done with hydrogen. Now with oxygen. Now when was it discovered? Oxygen was discovered individually by two different persons. Oxygen. It was discovered by two different persons. The first person was Skilly, and the second one was Priestley. Okay, this guy it's called Joseph John Priestley or something. This one is 1774. This one is 1772. Now, this guy, this guy discovered it. Okay, this guy was the one that even used them. He used mercury oxide to he heated mercury oxide and he produced oxygen gas. So you are going to see one of the laboratory preparations of oxygen as heating of some oxides. Now, I now said that now it was also named by the same guy, Antoine Lavoisier. He named it Antoine Lavoisier. Lavoisier. Okay, and he named it oxygen because he said it was oxy meaning acid, okay, because they thought it was the one because it was abundant in most of the acids that they found then. Do you understand? Both organic and inorganic, basically HNO3 and H2SO4. So they thought it was responsible for producing acids. So they called it acid. Gene means origin, that is former, right? Or producer, acid producer. You remember when we talked about oxyntic cells in my digestion video? Oxyntic, that's cell that produce acid. Now, oxy means acid there. Now, that's why he named it that way. Now, let's talk about some things you need to know about oxygen. Now, oxygen is the most abundant in the earth crust. Most abundant in earth crust. Earth crust. The earth crust has is composed of sand, right? And the chemical formula for sand is O2. Silicon, we have mass number of about 28 or thereabout, and this one we have 16 times 2, 32. So you see, it's just a little above 50% of the earth crust. Do you understand now? By mass. Now, oxygen is also abundant in water. H2O is the chief component of H2O. That is about 90% by mass also, because this one is just 2 and it has 16, okay, 16 grams per mole in water. Now, another thing you should now know is the allotrope of oxygen. We have dioxygen, which is our O2, and we have ozone, or ozone. And you have ozone, you have dioxygen. Now, dioxygen can be converted to ozone in the presence of ultraviolet radiation of the sun. Is that clear? So that's why it forms a ring around our head. Do you understand? So that ring that it forms is called the ozone layer. The ozone layer. Ozone can also be prepared from this by action of electricity. Passing electricity through oxygen gas is going to liberate ozone. Okay, it will make the oxygen, it splits the oxygen and make them become radicals and to combine them in threes like that, and you have ozone. Okay, so the point is that this guy is the ozone layer that is protecting us from the ultraviolet radiation of the sun, and it is depleted by greenhouse gases. We'll talk about greenhouse gases soon. Greenhouse gases. Example is CO2. Example is CFCs, chlorofluorocarbons. Don't forget to Greenhouse gas is CO2, not CO, not smoke, not carbon monoxide. All right. So we already know this now. Now, so these are the allotropes of carbon. Oh Jesus, I made a mistake. Please, for hydrogen, it is isotope. How did I make that mistake? I'm very sorry. For those um for those protium, deuterium, and tritium that we talked about, isotope. I'm very sorry. Um, Hydrogen does not have allotrope. Hydrogen has no allotrope. It has isotope. I probably even mentioned isotope as I was discussing, and I just remember that I made that mistake. Um, Oxygen has both allotropes and isotope because we have oxygen whose mass number is 16 and oxygen that's mass number is 18. Okay, but 99% of oxygen is 16, is the oxygen 16 that exists. All right. Isotope is the word iso means same, exactly. The word allo means another. Okay, I'm very sorry for that mistake. Isotope means top means unit. Is that okay? Unit. So they have the same isotope I've got. Those ones I wrote, you saw they have 88 as their atomic number, but different mass number. So they have the same atomic number, but different mass number. All right, let's talk about the properties, the physical properties of oxygen. What are the physical properties of oxygen? Now, number one is that it is colorless. Now, it is not totally colorless because liquid oxygen is actually pale blue, very pale blue, very pale, almost colorless, but it's very pale blue. Do you understand? This is a color, something like this. Something like this, exactly. It's not as deep as this though, but you know this is not totally colorless. Do you understand? So, but ozone is blue. Is that okay? Liquid ozone is blue, as blue as even blue, a little deeper than sky blue. You understand? Deeper than sky blue. So that is oxygen for you, but it is odorless and tasteless. It is odorless and tasteless. Now it constitutes 21% by mass of the atmosphere. So in the atmosphere we have that of this air. This air consists of nitrogen, which is 78%, oxygen, which is 21%, carbon dioxide, which is 0.03%. Is that clear? You see, you might think that I am rushing, but it's because of I don't want the video to be too long and the size of my phone memory. So let's be quick. We have water vapor, which is variable depending. You know that the atmosphere is humid in the morning, but in the afternoon is dry. So this one is variable, it changes. And this one, rare gases. Don't forget, rare gases or noble gases is 0.1, 0.03 for carbon dioxide. So it means that it can be prepared even from the atmosphere, from air. Exactly, that's one of the ways industrially we prepare oxygen. So here's the point that this guy constitutes 21% of the atmospheric air. Now, what else about oxygen? It is slightly soluble in water, or partially soluble in water because it actually can dissolve a little in water. But because the resolution is not absolute, also we can also collect it over water. Don't forget that we can also collect oxygen over water because it's not full, it's not a moderate or good solubility. So it is only, we say, partially soluble in water. Partially soluble in water. That's why for oxygen to mix with water, the water has to be turbulent. The water has to be turbulent, right? So partially soluble in water. What again? When I remember any other one, I'll let you know. Now let's go to chemical properties. Now, what are the chemical properties of oxygen? Now, oxygen is an oxidizing agent. That's the first thing. Because it's oxygen, so it will be oxidizing. It means it adds oxygen to anything. For example, you want to prepare this in the industrially, CO2. Do you understand now? It has oxidized carbon. Do you understand now? It has oxidized carbon. Also, nitrogen 2 oxide plus oxygen will give us what? NO2. And you balance out. Do you understand now? So that's the oxidizing property. The second thing is its reaction with lighted splinter. It ignites a lighted splinter. Don't forget, it ignites a lighted splinter. Do you understand? It ignites it. It will make it to glow more. Do you understand? If a splinter is burning mildly, softly, and you introduce oxygen gas to it, it will burn well. Do you understand? So it's used as a fuel also. And um, oxygen can also it reacts with metal to form their basic oxides. So we'll talk about oxides very soon. But before that, let's talk about their laboratory preparation. These are the parts that are being asked in your exam. So make sure the ones I'm not touching on is especially because I can't remember, and it's especially because they don't ask most of the time. So the ones they ask most of the time are the ones that I'm majorly talking about. Laboratory preparation. It is prepared by the thermal decomposition. Thermal decomposition. That is, we will heat up this particular salt and it will decompose to what? KCl and liberate oxygen gas. Do you understand now? Oxygen gas. So it happens in the presence of manganese dioxide. This is manganese 4 oxide. Exactly, manganese 4 oxide or manganese dioxide. Alright, so thermal decomposition of this guy produces that guy. So laboratory, the diagram will also look like this. We heat up our guy in a test tube. We heat it up in a test tube. This is our KClO3. We supply it. Now what will happen? We connect our tube to it, and we also collect it in a pneumatic trough. Also collect it in a pneumatic trough. Exactly. A pneumatic trough is used for what? For collecting gases over water. Don't forget, here all the air, oxygen. But the oxygen we collect will also be wet, so we can dry it using H2SO4. We use this guy to dry oxygen. Don't forget, we use this guy to dry oxygen. So this guy is also less dense than air. It's like oxygen is oxygen denser than air. At room temperature, oxygen is gaseous, right? So is it denser than air or is it less dense than air? I think it is less dense than air. Less dense than air. Meaning that if you want to collect it, if you want to dry it with hydrogen, you also collect it by upward delivery. Don't forget, upward delivery. Now, what if okay, there's also we can also prepare laboratory from higher oxides like peroxide, e.g. hydrogen peroxide. This is hydrogen peroxide here, H2O2. It also happens in the presence of what? It's also heated, okay? It also happens in the presence of manganese 4 oxide. If they tell you, how do we know that manganese 4 oxide is the catalyst for it? Is a catalyst and not one of the agents that is, and not a reactant there. Is a catalyst, not a reactant, because it is not used up. A catalyst fast tracks the rate of chemical reaction, but itself is unchanged. It remains unchanged. So this guy will give us water and O2. Exactly. Then O2 gas is also dried using H2SO4 in the same process I have mentioned. Then the one Priestley used mercury oxide, he heated it and produced mercury and oxygen. Do you understand now? So that was the way Priestley first produced oxygen. So that's the laboratory preparation. Now, what about the industrial preparation? The industrial preparation. Now, in industry, since that guy is 21% of air, then it makes sense to say that we can collect it, produce it from air, right? So we are going to collect air, liquid air in an aspirator. Aspirator is used to collect, don't forget, it's used to collect liquid air. Is that okay? A gas that has been liquefied is usually liquefied in an aspirator. So we have collected our liquid air here. Now, inside this place, we have all these components here. So you now pass it through a conical flask. through a conical flask that has that in which you have NaOH. Now, what is this for? This one is capable of reacting with carbon dioxide to form baking washing soda. It forms Na2CO3. Do you understand now? Then what we the remaining that will, so the what will be left that will go in here, we have what nitrogen and oxygen. This one has gone. Do you understand now? Do you understand now? So how do we now collect the nitrogen, remove the nitrogen so that it will remain only oxygen? Now it will not still remain only oxygen because you know water it will be passed over this thing to dry. H2SO4 will be here. Do you understand? To dry it. So this guy has gone. But real gas will still be there, 0.1%. And these two will be there. Now this is what will happen. You now take it to a trough, a place, a chamber where it will be heated. It will now be heated. Now that heating, this is the fraction, it's called the fractional distillation. You know, distillation is used to separate two miscible liquids. When liquids are miscible, you use this guy to separate them. Distillation. Fractional distillation here because they are fractions of air. They are part of air. So what will happen is that as you now heat them up, they boil at different temperatures. So one will go, as they are being boiled, when they get to their boiling point, they will be leaving. So and the boiling point of nitrogen is about minus 196 degrees Celsius, while that of oxygen is minus 183. You don't need to cram this, okay? You don't need to cram it. But the point I want to show you is that this guy will boil first before this guy. So once the guy boils, it will boil out. And what will remain is 99% oxygen. Exactly. Why 99%? Because these guys will still be there. Noble gases. So that's the point there. They usually ask about this guy. This one for drying and this one for removing CO2. Alright. That's it. That's the industrial preparation. Now, the very important part of oxygen. Oxides of oxygen. Listen, you must know this one. It will come out this year. Exactly. Now, the oxides of oxygen. The first one we want to talk about is the acidic oxide. The acidic oxide. So I'm not going to draw that periodic table again, but you know those metals that are here. Those metals that are on this side. Those metals here. We have acidic oxide, we have basic oxides. Acidic oxides are called acid anhydrides. Let me show you the meaning. An means not. Hydride means no water. So no water. So it means that they require water to form what? Acid. So oxides of non-metals are acidic oxide. Oxide of metals are basic oxide. So those metals here, they form basic oxide. E.g. Na2O, oxide of sodium, oxide of potassium, oxide of magnesium, oxide of calcium, oxide of aluminum, oxide of. So these metals here, they form what? Basic oxides. Basic oxide. While acidic oxides are oxides of non-metals such as CO2. Usually, the higher oxides are the ones that are what? Acidic oxides. So CO2 is the highest oxide of carbon. So NO2, not CO. CO is a neutral oxide. We have amphoteric oxides. See, amphoteric oxides are the ones that have the property of acid and base. Example is oxide of aluminum such as AlO3, zinc oxide, lead, and tin. Okay, lead oxide and tin oxide. These guys are what? Amphoteric. And copper oxide. They are all what? Amphoteric. The way to remember, alozoposoko. Exactly. So you remember, that's how to remember it. Then number 4 is neutral oxides. I'm trying to juxtapose, okay? Neutral oxides. The neutral oxides are the oxides, the lower oxides of this one. So for example, this guy will be neutral. Carbon monoxide will be neutral. Nitrogen oxide will be neutral. Dinitrogen 1 oxide neutral. Which one again? Neutral oxides, neutral oxides. So these guys are neutral oxides. Don't forget, they are not acidic. The ones that are acidic are these ones: SO2 acidic, SO3 acidic. Higher oxides are acidic. Lower oxides are what? Neutral. Don't forget that. Higher oxides acidic. Neutral oxides are the lower oxides. All right. Now, then we now have the what we actually call the higher oxide. This higher oxide of non-metal that I mean, okay? Then we now have the higher oxide. They are also called peroxides. Okay? Higher oxides are peroxide like H2O2, Na2O2, CaO2, barium oxide. These guys are what? Higher, they are called peroxides. They are the higher oxides. Alright, so that is it for. Take note of this part, please. Especially the amphoteric oxide. Amphi means two, like amphibian. It means two sides. Exactly. So they can behave as both acidic and basic. Master it, allosoposoko. Exactly. Alright. So the uses of oxygen. We use it in preparation of for oxyacetylene flame. Don't forget, it is used for oxyacetylene flame, and it has a lot of use. That is, it has a lot of use for breathing, for respiration, for production of contact process H2SO4. Do you understand now? Because we lose sulfur in air, then add that sulfur to H2O to form H2SO3, then add that to already prepare H2SO4 to form H4, this guy, that's oleum. Oleum will now be heated to give H2SO4. So now, oleum will be added to water rather, not heated. I'm sorry, I'm rushing. So, okay, so let's continue. Chlorine. So basically, let's talk about halogens. So we're talking about chlorine now. It's chlorine we usually want to talk about. Now they are called halogen. The word halo means salt, and gene means former, salt former, like we have said. Now, what are the halogens? Halogens are the guys that are in group 7. Halogens are the guys in what? Group 7. If this group 8, group 7 will be here. Exactly. So in this group, as we have helium here, we have neon here. Here we now have fluorine, chlorine, bromine, iodine, astatine. Exactly. These guys. Now there's something, that's also what I want to show you, a trend that we see here. Fluorine is pale yellow in color. Let's talk about their color first. This one is greenish yellow in color. This one is brown in color. This one is deep blue in color. This one is black or very deep blue too. Okay, in color. You see that the grade of their color is deepening. Just now is deepening. Then also reactivity. This guy, because it has the smallest atomic radius, it is reactive than all these guys. It is the most electronegative element in the periodic table. Fluorine is the most electronegative element, or the most reactive non-metal. That's fluorine. Do you understand now? And as you go down now, their reactivity decreases. So this guy will be more reactive than this, guy will be more reactive than this, guy more reactive than this. So this guy can displace this guy from a solution of his salt. For example, F2 plus Cl2 plus NaCl, for example, will form MaF plus Cl2. Do you see the way this guy displaces this guy? When he got here, he just like, get out of this place. I've come because it's the boss. Do you understand? Why are they more reactive? It has a lower atomic radius, means that the charge of the nucleus is positive because it's proton which is positive charge and neutron which is zero charge. That's plus. So that's why that's how the nucleus is positively charged. So that positive charge is attracted to electron faster than the one that is triple shell. For example, chlorine shell is like 3 shells, so its atomic radius is wider. So the attraction will not be as much as fluorine, that the atomic radius is shorter. So it will be able to get electrons faster than the remaining ones here. Is that clear? So those are the things we see with their trend in their reactivity and like that, and their color. What else? Then their physical properties. This one is gaseous. These two are actually gaseous, but this is a heavier gas than this. Is it making sense now? Gaseous at room temperature. This one liquid at room temperature. Solid, volatile solid at room temperature. This guy is known to undergo sublimation. Don't forget, there are 2 questions you normally ask about sublimation. is with CO2 and I2. Both of them can sublime at room temperature. This one is called dry ice, in case that's what is given to you. Sublimation is the process by which something goes directly from solid to what? To the gaseous state. If it returns, is deposition. Then from here, sublimation. Here, deposition. Oh, so that's the point. Iodine can sublime. All right. So it is solid at room temperature but volatile, and while astatine is solid, although soft solid, but solid at room temperature. So you are seeing there that their boiling point is increasing as you go down, increasing boiling points. The first two are negatives. Bromine is positive 58.8 degrees Celsius. Okay, so that's by the way. Now let's go to now let's now treat chlorine itself. Chlorine was discovered by Skilly in 1774, and it's called chlorine from the word chloros. Chloros means greenish, and it's because of its greenish yellow color. Anytime you hear chlorophyll, that's greenish. Phyll means leaf. Phyll means what? Leaf. Phyllo is the Latin for leaf, so green leaf, that's of chlorophyll. So here, chlorine means greenish gas. Exactly. That's why the color is greenish yellow. All right. And it is reactive. How is it prepared in the laboratory? No, let's talk about the physical property. Greenish yellow in color, it's 1.7 times denser than air. So because of that, it will be collected by what? Downward delivery. Now it is prepared by the action of HCl on MnO2. Okay, this guy will give us MnCl2 plus H2O plus Cl2. There's no time to balance, just try and balance it by yourself. So now you see that water is produced. Okay, 4 gig. Okay, 0.1 hour. Okay, so chlorine, you see that water is produced, so it means that the gas has to be dried, right? So you have in your jar your chlorine, this mixture will be here, then it will be passed into another cylinder where we have H2SO4. No, first we will have yes, H2SO4. This H2SO4 is to dry the gas. The H2SO4 is to do what? Is to dry the gas. Did I make a mistake here? MnCl2 plus H2O. Yes, H2O is to dry the gas. Exactly. No, it will not be connected. It's to dry the gas. This guy. Then we'll now have also, see, listen, there's also another gas here, another cylinder here where water is. In fact, that one comes before the acid, but you can do it either ways. There's water. Why? Because see, laboratorily, some HCl gas will still move with it. So the HCl gas will be collected here because HCl is very soluble in water. So because it's soluble in water, it will dissolve here. And what you have inside your gas jar is your dry gas, your dry Cl2. So we use this guy to dry chlorine gas. So that's what you need to know about that. Now let's go to this. So that's the laboratory operation. It's also prepared by the action of the same HCl on KMnO4. Depending on the one you see in your exam, exactly. Some will give us KCl plus MnCl2 plus H2O plus Cl2. Exactly. So you should just balance out. Now, that is that for that. Now let's go to the industrial preparation of chlorine. And if there is industrial preparation, it should just be the direct combination of H, hydrogen plus Cl, okay, and it burns in it. It burns. It reacts with by burning, okay, in the presence of sunlight. The reaction takes place in the presence of what? Sunlight, and it produces so is HCl that actually produces, not Cl2. Not Cl2, sorry. I think because I'm rushing, I'm missing some points. But don't worry, all the details I'm giving you are they are correct. I'm just misplacing some things because I want to rush. Now, Cl2, Cl2. Please subscribe to the channel. God will bless you and share the video with your friends. Just subscribe, okay? Subscribe. God bless you. Please subscribe, okay? Now, let's go to we have done the laboratory operation. What about the um, chemical properties? Chemical properties of chlorine. Now, the chemical properties, it can react directly with hydrogen to form HCl. Exactly. I told you it happens in the presence of sunlight. Now, they normally ask this, but the other thing they normally ask is this one. It's bleaching property. It has a bleaching property. Now, the bleaching property of hydrogen is if you react first, hydrogen is used as chlorine rather is used as a disinfectant, okay, for pool. Disinfectant in pools and municipal waters. If you use it to, that's for purification of your water. So what it does is it kills bacteria. How does it act? If you prepare the diagram is somewhat like this. If you put this guy inside water, so chlorine is here, in the presence of sunlight, chlorine gas will react with water. So the reaction goes like this. When they react, it's going to form HCl and hypochlorite. HCl and hypochlorite. Hypochlorite is also called oxochlorate 1. Now this guy has bleaching property. Now how does it bleach? It's going to your hypo that I used to wash. This is the formula. So this is the chief component. So when it dissolves in that water, HOCl will now break down to HCl plus O2. So it's the liberation of oxygen that gives it its bleaching power. Don't forget, it's when it liberates oxygen that is able to bleach. Exactly. That's able to bleach. So that's that for chlorine there. That's the bleaching power of chlorine. Now let's quickly talk about it also react, it is a good, it can displace, I've talked about that, it can displace its lower guys. Bromine will displace iodine displace, you understand like that. Now, another thing you should know is now the for chlorine, the test for chlorine. Now, the test for chlorine is damp litmus paper. If you use a damp litmus paper, if the litmus paper is damp blue litmus paper, it will turn red. It turns red and bleaches. The turning red is because of that. I told you it's damp. If you dampen it with water and you react it with this, that chlorine will react to the water and form HCl, which is an acid. So it turns blue litmus paper to red. But I told you it has bleaching property again, right? So it will now bleach it white to become white. Number 2 test is this with normal blue litmus paper to just bleach it. Now, number 2 test is with starch iodide paper. So because it displaces iodine, it's going to from blue black color, it's going to become white. It will bleach white. Exactly, to show you that chlorine has taken, when you use starch iodide paper, chlorine will displace this guy and take the place, and iodine will be given off and it will be bleached. Exactly. Now, see, I'm just cleaning this place and doing it here. Because of the time. What again? So that's basically it for chlorine gas. Now let's deal with HCl, which is one of the chief components that is produced with chlorine. The chief substance that we use in laboratory. HCl is called the mixture of HCl and HNO3 in the ratio 3:1 is called aqua regia or regia, whichever one we call it, aqua regia. Exactly. HCl is ratio 3:1. Exactly. Aqua regia. So don't forget that. This one alone is called aqua fortis. Now, what you'll notice about this guy is they put aqua in their name. Both of them are very soluble in water, very soluble in water. So HCl is soluble in water as much as HNO3. So that's why it is used to perform the fountain test experiment. Fountain test experiment or fountain experiment, that was you call it. Now the fountain experiment, the criterion for performing the fountain experiment is solubility in water. So because this guy is soluble in water, can perform it. The other one that can be used is HNO3 and ammonia. Those guys are soluble in water. The test for HCl is that if it's acidic, but if you react with ammonia, it will first form N2 and no ammonia, sorry, NH4Cl2, NH4Cl. Ammonia is one. So NH4Cl, and this shows dense white fumes. Okay, dense white fumes. So that is, if you have ammonia, you react it with the unknown gas, and it forms dense white fumes. Then that is the gas. The unknown gas is HCl. All right. That said, other function of chlorine is in the use of PVC and production of PVC, exactly, polyvinyl chloride, and tetrachloromethane, exactly, and um, trichloromethane. That is the one we use for anesthesia. Now, that's all for halogens and chlorine. Let's quickly talk about nitrogen. Now, nitrogen was discovered by Daniel Rutherford in the year 1772 as well, Rutherford, and it was also named by Antoine Lavoisier, and that nitro means saltpeter, and G means former. Now, what about nitrogen? Nitrogen is 78% of the atmosphere. It means in the atmosphere, nitrogen gas is the most abundant. Don't forget, nitrogen gas, 2.9. Nitrogen gas, yes, we can finish it before time. Let's go. Nitrogen gas is the most abundant, 78%. And that's in the atmosphere. So it means we can prepare from the laboratory, from the atmosphere industrially. So I'm going to show you. Now, nitrogen is inert. It's relatively inert. Why? Because of the strong covalent bond holding it. The other gases we did, single covalent bond holds this guy. This one, double covalent bond holds this guy. Single covalent bond holds this guy. But this guy, triple covalent bond. So it's very strong, and the bond energy is high. So it's not easily broken. So because of that, it is inert. It is inert. That's why nitrogen gas does not necessarily have one big chemical property, because yeah, it has some chemical properties, but it's not reactive because it's very stable, very stable. Now the other thing is that it is slightly less dense than air, slightly less dense than air, and it is it is not soluble in water. Then it has a boiling point of that 196 degrees Celsius and a melting point of 300 and something, minus 300 and something degree Celsius. So those are just physical properties. It is colorless, odorless, and tasteless. They won't ask you that in the exam. I'm just trying to, Now let's talk about chemical property. The chemical property that you should know is that magnesium ribbon, when you react it with this guy, to form magnesium nitride. Exactly. Magnesium nitride. Okay? So that's that. Another chemical property is that industrially it is used to prepare ammonia. When you combine these two together in the presence of finely divided iron catalyst, we'll get there to form ammonia. We'll get there now. So now in the industry, how is it prepared? We'll get our liquefied air to here. Okay? We'll bring it here. Then we will now pass that air over it will first pass over, yeah, it can first pass over that NaOH that I drew, yes. When it passes over NaOH, it will remove, N2, O2, CO2, and rare gases are the ones in the atmosphere. So NaOH will remove what? CO2, don't forget. Then we don't need oxygen now. So what will remove oxygen? There are two things that can remove oxygen. Is either you use alkaline pyrogalol, because there is acidic one, pyrogalol. Is that clear? Alkaline pyrogalol will remove oxygen, or use copper turnings. Copper turnings. What are copper turnings? Copper turnings are just tiny chips, tiny chips of calcium, of copper rather. So you can pass it over here, for example. So it is heated, or it will be heated, exactly, to make them reactive. Okay, you heat copper turnings here. This is copper turnings, and when it is passing over it, CO2 has left. It's now remaining 1, 2, 3. So this one, when it passes over here, it will reduce. It will oxidize copper. It will oxidize copper. Then this one has left now. This one has left. Now it will now remain nitrogen and rare gases. So that's what you now collect. So the nitrogen you prepare to that way is not 100% pure. It still has some about 1% rare gas. All right. That's the preparation of nitrogen. Now let's go to the compounds of nitrogen. Number one is ammonia. Ammonia it has a pungent and choking smell, like chlorine. Yes, please. Chlorine has a choking smell. Ammonia also has a pungent smell. That's the way we describe it. One is pungent, the other is choking. Chlorine is choking. This guy, ammonia, is pungent. Ammonia is NH3. Now, industrially, it was Eber Fritz was the one that prepared it in 1940 something, during the Second World War. That's between 1939 and 1945. So that was when. So Eber Fritz prepared it by this process, N2 plus H2 to give NH3. To give NH3, you balance it this way. Now listen. It's a reversible reaction. Now Fe, excuse me, finely divided ion catalyst is the catalyst. Finely divided ion is the catalyst. Is that clear? Finely divided ion is the catalyst. Now when I forgot to mention this one. CH4 plus H2 that we use to prepare hydrogen. The catalyst is nitrogen, okay, at about 300 degrees Celsius and maybe 30 atm. But remember, this one is nickel catalyst. If you see my video on organic chemistry, I've done this. I've showed you this before. Okay, so this one is finely divided ion catalyst. No nickel, no palladium, finely divided ion. Now we produce this guy. Ammonia has basic property. Ammonia is a base. Ammonia is what? Is a base. Don't forget, ammonia is a base. Right? Then what is again? Ammonia has reducing property. Because of course you see this, so it has reducing property. For example, if you react ammonia with HCl, we said that to give us NH4Cl, and if you react it with NH with acids, H2SO4 for example, to produce NH4 to SO4. Okay, so that's the reaction with acid. Okay, so they react with acid to give you salt. That shows that they are bases. Exactly, base plus acid to give you salt and water. Now, what else about ammonia? The test for ammonia will just be the reverse of what we talked about for HCl. HCl will, if you react the unknown gas with HCl and it gives you dense white film, and that gas turns red litmus paper blue. That is ammonia. Exactly. That is ammonia. Produces dense white film with HCl. That's ammonia. Now, there's something I wanted to say with this ammonia, but I've not remembered. Let's go to the next thing there. The oxides of nitrogen. The oxides of nitrogen include NO, the lowest one, N2O, NO, NO2, N3, N2O3, N2O5. Now, learn it this way. Their oxidation numbers here are 1, 2, 3, nitrogen 4 oxide. 1, 2, 4, this will be 3 here then. So let's put this one first. N2O3, 3, nitrogen 4 oxide, NO2, 4 and 5. Exactly, that's how to remember it. This is the highest oxide of nitrogen. This one is just a nitrous, um, acid, is an acid anhydride. Exactly, it's from nitrous acid, HNO3. Now there is something I wanted to say about preparation of nitrogen. I forgot. The way we prepare laboratory is we break down catalytic breakdown of NO dinitrogen of ammonia dioxonitrate what will it be now? Ammonia 1 plus X minus 4, that will be 3. Dioxonitrate 3. So when this guy breaks down, it will produce nitrogen and water. So it breaks down to give you nitrogen. Don't forget that. So because this question has come up before, this guy breaks down to what? Then I'll give you about nitrates, how they are used to produce this thing too. I'll give you something with that nitrate using that, reactivity series. Now let's quickly talk about this. This guy is called dinitrogen 1 oxide, dinitrogen oxide, or nitrogen 1 oxide. It is called laughing gas. It is when inhaled, it induces a laughing sensation. It is a neutral oxide. This guy is neutral oxide. This guy is nitrogen 2 oxide. Exactly, nitrogen 2 oxide. This one is nitrogen. This one is also an acid anhydride like this one, and this one is the highest. This one is colorless and colorless. This one has brown color. In fact, there's another oxide that is unstable, N2O4. This one is yellow. Okay, it is formed momentarily and it always reverts to NO2. Okay, and it has a yellow color. Then the yellow color will change to brown, which shows that NO2 has been prepared. NO2 has been formed. NO2 is the highest oxide of nitrogen. Highest oxide, NO2. Now, excuse me. NO2 is an acidic oxide. Okay, so I hope you understand that it's an acidic oxide. Now, let's talk about the nitrates. Let's talk about HNO3. HNO3 is a very strong acid. This one is called aqua fortis. So it shows you that it is soluble in water. It means strong water. That's not aqua fortis. Now, it's very soluble in water. It means it can also be used to perform what? Fountain test experiment. There's something that is coming to our mind that I feel I should mention. Gibbs apparatus is used for continuous supply of a gas. In the laboratory, when the continuous supply of a gas is needed, Gibbs apparatus is used. Don't forget. Gibbs apparatus just comes in layers like this. Do you understand? So, I don't know why I mentioned it. It kept coming to my mind. So, now, HNO3, listen. But fountain test, when you have a diagram like this, and you now see something like splash of water coming like this, that is fountain test. Is that clear? So you'll be asked, they'll give you the diagram and your exam will now say which gas or which compound can be used to perform this experiment. Is that you see HNO3 there, HCl or ammonia? Either of those will be the answer. Now, HNO3, the test for HNO3 is an acid. The test for HNO3 will not be turn red litmus turn blue litmus red only, because many other acids do that. This one particular test is called the brown ring test. The brown ring test. In the brown ring, we will add, if we have HNO3 here, we will add FeSO4, iron sulfate, and H2SO4. It will form a brown ring of a double salt. That brown ring shows that the first salt, the first compound that was there was HNO3. That's what we call the brown ring test. Don't forget the things I said we had. First, HNO3 is already there. We had FeSO4 and H2SO4. And then, H2SO4. Now, that's that for HNO3. HNO3 is used for the manufacture of explosives. Don't forget, explosives and fertilizer. We also use ammonia for fertilizers, manufacture of fertilizers. This one for explosives. Trinitrotoluene. That was especially why it was manufactured in the Second World War. Americans used to manufacture trinitrotoluene, a major component of explosive. Trinitrotoluene. What else? Now, other nitrates. Now, listen, these nitrates. Let me see. We have less than a gig. Okay, let's see how fast we can rush carbon. So now listen, you see those first two that are in the reactivity series. They are nitrates. When they are nitrates, break down. It will form KNO. It will form, let's call them X. The remaining ones down to lead, let's call them Y. Then from H, below hydrogen, let's call them Z. When these ones, when they break down, they will form XNO2 plus O2. The way to remember that, I'll show you. Then this one will form YO2 plus NO2 plus maybe O2, and yes. Then these ones, they break down to form K, they will form themselves, and O2. This is how to remember. That these guys are very strong, they are reactive, that they will never leave their NO2. They are nitrates. So instead of leave nitrate, they will stay with nitrite. This is called nitrite. This one is nitrate. Just now, then oxygen. But the rest, these ones are not as strong. So instead of, they will leave their nitrite, they will let their nitrite NO2 go, but they will still hold on to the oxygen. Is that clear? Don't forget. Then these ones, they cannot hold on to anything because they are weak. Is that clear? That's how to remember. Good. Let's quickly go to. So for example, if I say show me for lead. Lead will be, lead nitrate will look like this. PbO plus NO2 plus O2. Exactly, that's the way it's going to break down, undergo decomposition. Now let's go to carbon. My phone memory is almost gone. Carbon. Now carbon is one of the longest living elements in the universe. It was discovered, a particular allotrope of carbon was discovered in the Carboniferous era. That's about 4.5 million years ago. Carboniferous era. From volcanic remains of volcanic eruption. Okay. Now, carbon has allotropes. There are two major allotropes, two types of allotropes. We have the crystalline allotrope. The crystalline allotropes are the allotropes that have structure, they have form. Then the one that don't have form are amorphous. The one that amorphous there, means not. Morph means form. So no form, they are shapeless. So the two crystalline ones that you know are diamond that exist, are diamond and graphite. And I've told you some things about them. The difference is that diamond cannot conduct electricity. Graphite conducts electricity. Diamond has an octahedral shape. This one has hexagonal shape. In fact, this one is a 2D structure. But the 2D structure, they are now held together by van der Waals forces. Do you understand? We have another one here like this. So you understand? So they are now on different layers like that. But this one is a 3D structure. This guy is the hardest substance known. This one is very soft. This one, when you heat it to about 900 degrees Celsius or so, you are going to make diamond. So the graphite can be used to manufacture diamond. Graphite conducts electricity. And if you add it to clay, use it to make pencil, lead pencil. Use to make your what? Lead pencil. And the percentage of Clay is what determines the softness of a pencil. Soft pencils have a lot of graphite, high graphite, low clay. High clay, low graphite means hard pencils. All right. Soft pencils will be darker. Do you understand now? Okay, so that's that. Then the amorphous carbon are coal, okay, charcoal such as animal charcoal. We have animal charcoal. We have wood charcoal. We have um, we have wood charcoal. We also have sugar charcoal. This one I can remember. Then we have lamp black. Lamp black. Now don't forget, and carbon black. Carbon black is the one we use in printer's ink. Using what? Printer's ink. Then lamp black is called soot. Don't forget. Carbon black is the one that is used in printer's ink. You know that thing that they buy for inkjet that they pour inside that they used to refill this thing, photocopy machine. So that thing that printers to use, printing machines, that's carbon black. Then lamp black, so that's the one that they use to write. Then this carbon black, this is the one that they use to print these things. Exactly. Then lamp black is soot. Soot, lamp black is this. So if you know lantern, you know this thing. It now has this thing here, it has a frame structure here, then it has a cap. So your light, then there's something here, then your fire will burn like this. Now, you remember that if you don't regulate it well, what will happen is that it will stain it, it will form black stuff there. That black stuff is soot. Another place to see soot is if you go to the silencer of your father's car, you touch the inside, you see those black stuff. That is soot. Now, for coal is an allotrope of carbon, an amorphous allotrope that undergoes destructive distillation to give coke, coal tar, coal gas, and ammoniacal liquor. And it's not liquor, it's liquor, the sound, let's use short sound. Now, then, animal charcoal is just burning this thing, limited supply of oxygen. This one is called decolorizing charcoal. The animal charcoal is called what? Decolorizing charcoal. It decolorizes methyl orange. Exactly. Wood charcoal is burning wood in all of them. They are in burning things in limited supply of it. Wood charcoal is you can make it yourself. You dig a pit, pour wood there, put petrol, light it with fire and cover it up so that oxygen does not penetrate to form wood charcoal. So that's wood charcoal. Then there's also the distillation of destructive distillation of wood. That one gives I think coke also. It was wood tar. See, this is where I remember mine sometimes. I just say wood tar, wood gas, and pyroligneous wood. Look at my video on organic chemistry. I talked about the components of the pyroligneous wood. Okay? So that is that about that. Now let's go talk about the oxides of carbon. Okay, I still have up to. Okay. Now the different forms of coal. We have anthracite, peat, lignite, and bituminous coal. So they have different percentage of carbon. So make sure you look it up. Check it, please. Then I don't want to begin to think. The next one I want to do is what we've done the allotropes of carbon. The oxides of carbon. The oxides now. Production of carbon laboratorily is by in the industry. Coke. The destructive situation of coke. We use it to prepare carbon. We also use it to prepare of coal to prepare carbon. So this is carbon. Coke is carbon. not Coca-Cola, please. Is that clear? Now, sugar is the one we call sugar beet. It is formed when you heat up sugar to brown. Okay. Oxides. Now we have carbon monoxide, carbon dioxide, and carbonate. Now, the carbon monoxide is number one, it is neutral oxide and it has a choking smell. This one, it attacks hemoglobin. It attacks hemoglobin, your hemoglobin. Why do you say it attacks hemoglobin? You know, hemoglobin in your blood, your RBC, is one that carries oxygen. So it has oxygen on it. So when that, if you are in your room where they are burning and you did not leave, that carbon dioxide will go into your lungs and trap or remove oxygen, go to your blood, take oxygen. Do you understand now? So that's how you say it attacks hemoglobin. So the person might die. This one too. So this guy is poisonous. So I remember chlorine is also poisonous. Don't forget, chlorine is also poisonous. Then you say, why do we use it to purify pools or even water? We use them in very tiny quantity. It kills bacteria. Exactly. Now about CO2 is also bad, but only in higher concentration. The only thing about CO2 is that it's a greenhouse gas. That's what's bad, mostly bad about it. It depletes the ozone layer, CO2. And this guy has reducing property. It gets oxidized. CO plus oxygen forms CO2. Exactly. Then carbonates. Carbonates are salts that contain CO3. Exactly. Now you see these carbonates, they so that's one of the way by which is if you react carbonate with acid, that's one of the way by which you can produce CO2. Exactly. Any acid, anytime you react a carbonate with an acid, don't forget you produce water, you produce a salt, any salt, for example here, you produce NaCl, water and CO2. Usually that's the question, that's one thing that's the component that they want you to find out there. CO2. Is it clear? Now, um, the test for CO2 is that it turns lime water milky. Now, what is lime water? Lime water is calcium hydroxide. How do we get calcium hydroxide? From quicklime, from CaO. When you add it to water, this is called slaking of lime. So this is called slaked lime. So this lime water, if you react it with the unknown gas and it forms CaCO3. You know CaCO3 is marble or limestone or chalk, right? At least you know chalk. Color of chalk is white. So it forms a milky precipitate of CaCO3. CaCO3 is insoluble. In fact, all carbonates are soluble except sodium, ammonium, sodium, potassium, and ammonium. I use this thing to teach you. SPA, sodium, potassium, ammonia. All their salts are soluble, including carbonates. But every other carbonate is insoluble. Don't forget, every other carbonate is what? Is insoluble. So this will be it for this video. And the test for this guy, carbonates, there are different tests, exactly. But usually they form precipitate, so that's why I'm not dealing with their test. Usually they use barium sulfate to test for it. Barium sulfate plus a particular carbonate. It will form a carbonate that is not like a whitish, for example, BS2CO3 is insoluble. So, and it forms a whitish precipitate. And that is an insoluble salt. Exactly. See my video on solubility of salt. You will understand all these things I'm talking about. God bless you. Do want to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. God bless you. I thought I was going to do like 2 hours. Wow.